Hello there, children. Today we are going to work on the Chapter 8 review. So, let's take a look here. So this first problem is a log problem. Now, you will always be graphing the points 1, 0, and a, comma 1. Now, in this case, a is the base, so a is 6. Now, what we have here is 1, 0, and 6, 1. Now, this negative 5 on the outside will move your graph down 5 units on the y. So we take our 0 minus 5, giving us negative 5. 1 minus 5, giving us negative 4. Now this inside transformation does the opposite. So it's minus 1 here. We are actually going to go to the right 1 unit because you will need 1 more than you used to have to get the same value on the inside. So instead of a 1, we have a 2, and instead of a 6, we have a 7. Now since I moved to the right 1 unit, I will also need to move the asymptote to the right 1 unit, making it a 1. Notice how I have a vertical line here, and it is labeled. Now, if I continue moving on to the next problem, same thing here. We graph 1, 0, and a, comma 1. A here happens to be 5, since the base is 5. So I have 1, 0, and 5, 1. Now this negative 3 transformation will go down 3. So my 0 becomes a negative 3, and my 1 becomes a negative 2. I then go, since it was plus 4, I move to the left 4 units, so I was at 1, now I'm at negative 3, and I was at 5, now I'm at 1. Since I moved to the left 4 units, my asymptote also moves from being at 0 to now negative 4. I can label it. You could also write it over here, folks, if you wanted to. Just write asymptote x equals negative 4. It is very important you put the x equals. If you don't, you will lose some credit there. Vertical dotted line. Now let's keep scrolling. Now, these particular problems are exponential functions. Now, here you can go back to creating a t-chart. I personally use 0, 1, 2, negative 1, negative 2. You can pick whatever numbers you want, but picking a number like 70 billion would probably be a very silly choice because it's off my graph. So, this one here denotes my y-intercept. No, it denotes what? Asymptote! Very good, imaginary voice in my head. It denotes the horizontal asymptote. So it is a y equals since it's a horizontal asymptote. So I then scroll and I plot these points that I put. Remember, you pick your x values into the function to get y. You plot your points, nice smooth curve. Again, don't cross your asymptote and make sure it is labeled. Let's move on. Now this particular problem, I again create a t-chart. I picked negative 2, negative 1, 0, 1, and 2. Now, these are probably excellent selections, but you again can pick other points if you like. I just like keeping it simple. Keeping it real. So I put these x values into my function and I get y values back. Now this negative 2 on the outside here denotes my horizontal asymptote. I mark it with a horizontal dotted line and I put the value y equals negative 2 in there. That is how I deal with that. Notice I label it and notice I have a smooth curve. Now, my picture is not the best thing in the planet. It's more like a blindfolded 5-year-old with a crayon. Thing about it is I have a t-chart over here backing me up. And the graph looks somewhat accurate. I mean, it's not the best drawn thing on the planet. I'm not going to win the art show by any imagination, but it'll do. That'll do, pig. That'll do. And I have backing with a t-chart, so I would earn full credit. Now, scrolling on here. Expand each log. The first thing I want to do in an expansion is, if there's an exponent here, share, because sharing is caring. Thank you, imaginary voice in my head. You're being very helpful today. So, I multiply here, I get a 4. And a 20. Now, once I distribute that, and I'm trying to look to spread it apart, I need to break up multiplication or division with the product or quotient property, respectively. Luckily for me here, this is a multiplication, so I spread apart with the quotient property or the product property. It's going to be product because product is multiplication. So that means put an addition sign in the middle. Log base 4 of u to the 4th, log base 4 of v to the 20th. Now I'm not done yet. I then take the exponents and drop them out in front as coefficients. Oh, happy days are here again. Let's keep on trucking. This particular problem means condense into a single logarithm. Now remember, we talked about when you have a division and it's not inside the log, so dividing a log by 3 is the same as multiplying a log by 1/3. Now, here, when you're condensing or bringing back together again, what you're going to do is take your coefficients and bring them back up as exponents. That's why the 2 comes up here and the 1/3. And then you can Humpty Dumpty this back together again with the plus sign turning into multiplication. Now notice here, I have a u to the 1/3 or I have the cube root of u. Here's the thing, folks. Both are the same thing. It won't matter which one you do. You'd earn full credit for this or that. But realize also, if you're expanding and you have a cube root, it really is u to the 1/3, and you need to drop that exponent down out in front if you are expanding. Moving on. Solve each equation. Now, this equation, I want to make sure I make the bases the same. Now, unfortunately, I cannot make 125 25 to some power. Not possible for me. Luckily for me, I can make 25 5 squared, and I can make 125 5 to the 3rd. Now, when I have a power to a power like this, I multiply those exponents, giving me 6v. I then look, I have 5 to a power, 5 to another power. If the bases are the same, these exponents must be equal, and I can solve. Moving on. Get ahead of myself there. Super excited for math today. This problem, number 8. Well, solve each equation, round your answer to the nearest 10,000, which means 4. Count it 4 decimal places. So before I can do anything here, I need to get this base by itself. What I do is I get rid of any coefficients out in front or any numbers behind it, like a +7 or a -12 or something like that. So here I have a -6.1. It's attached with multiplication. I must divide it over. Now I get to this, and I ask myself, is the thing with the exponent by itself? Means, is the base number all alone? And the answer is yes. So therefore I turn this into a log. It's all about that base, and no exponent. So what I do is I make the log base 9 because the base of my exponential function is 9. I then take these two things and flip-flop their positions in the problem, or loop around here and go base 9, grab that number, equals that. Now from here, folks, this is change of base formula. It doesn't matter if you do this or this. The reason I use change of base again is because most of your calculators cannot do anything but base 10, which is log, or base e, which is ln. So therefore, I have to switch it in this. If your calculator can do this, please skip to this step right here. Now notice how I didn't round here yet. I will round at the very end of the problem. These numbers equate to this. Subtract 2 to solve for n, and I round to the 4th decimal point. Moving on. Solve here, round to the nearest 10,000s. Okay. Woo! Get hyped for math. So what I do here is I have a -6 out in front and a -8. Remember, you do order of operations in reverse. So I'm going to add 8 to both sides, giving me 50 because it was -58 plus 8. Then I divide by -6, giving me that. Under no circumstances can you multiply that -6 by that 14. You will get a wrong answer pretty much every time. Don't do that. Okay. Now, from here, I turn this into a log base of 14 because the base of my exponential was 14. Here, this is change of base again, or if you can go from your calculator and put in different bases, go right to here. I then subtract 6 from that number and divide by -10, and then round to the 4th decimal point. So 59195. There's a 5 right there. All right, so it's 51965. Remember, 5 and above, give that number a shove. 4 and below, let it go. That's why it becomes a 7 and not a 6. Here, solve each equation. All right, big thing here. If you have log equaling log, I can cancel them out provided the bases are the same. And I get left with the gooey nougaty interiors here. So what I do is I set these equal to each other, because if the bases were the same, these must be equal. Same with, by the way, this problem all the way up here. If the bases were the same, the exponents must be equal. This problem, if the bases are the same, the insides or the arguments of the log must be equal. Now, what I do here then is once I get k equal -12, I'm not quite done yet. I must check it in each inside of these logs to make sure that the inside of the log is not 0 and is not negative. If it is, that's not a good solution. Luckily here, if I put -12 into both of these, they both work. So I'm good to go. Moving on. Now again, I have log equaling log here, so I cancel them out. Unfortunately here, I'm left with a quadratic. How do I know it's a quadratic? Well, I have this squared term. So I set it equal to 0 because I have a squared term. Now when I do this, first thing I check is for a GCF. Luckily here they both have k's in them. I pull that k out. If there were another number here, like a +7 or something like that, I would then either factor this and set each factor equal to 0, or I use the good old-fashioned quadratic formula. So you can go from there. Now here I set each factor equal to 0. So k equals 0 and k minus 5 equals 0. The problem with k equals 0 is when I go to check this in one of these logs, I get k squared minus 2 equals 0. I put a 0 in there. 0 squared is 0. 0 minus 2. It's over. I got a negative inside of one of my logs. That's not good. In fact, it's so not good, 0 can't be an answer. So cross that one out. Let's try 5. Luckily, when I put 5 into both the insides, I end up getting a non-zero number and a number that's positive, which means it's a good solution. So I thought I had 2 answers. Turns out I only have 1. Over here, number 12. Now, unfortunately, I don't have log equal log this time. I have 2 logs on one side and no logs on the other. What I need to do is Humpty Dumpty these back together again. It means condense them. That's why we did all that condensing work earlier. So I condense them. Now, this is a subtraction sign, which means I write this as a numerator, that as my denominator, and 1 log out in front. Now, when I have 1 log equal to a number, folks, I turn it into an exponential function. 5 to the first power equals this. Multiply both sides by 6 and subtract 5 here. You get x equals 25. And luckily, it doesn't make the inside of this log negative, and it doesn't matter there because that's a constant number, so I can't make that negative anyways. Huzzah! There's my answer. If this number didn't work, you would then write no solution because I thought I had an answer that worked, and it turns out that I didn't. Now, over here. Again, need to condense these because it's 2 logs on one side of the problem. It's a plus sign in the middle, which I condense with multiplication. 4x squared times 9 gets me 36x squared. Since it's 1 log equaling a number, I then turn it into an exponential function. 6 squared equals this. Remember, this should never look like this when you turn it into an exponential, which means you did it wrong. 6 squared is 36. I then divide by 36, getting me x squared equals 1, and square root. When you square root a variable, folks, you need to put plus or minus. Luckily, when I check plus or minus 1, it makes this non-negative and not 0. So 1 and -1 are good answers. I have 2 of them. Oh, happy days. Now, we deal with a banking problem. Mr. Chadwick Boseman decides to deposit money into a bank. He is depositing $145,000 into an account with 0.35% interest rate. I guess Wakanda gets great interest rates. Chadwick picks an account with compounds interest quarterly and things like that. So he'll leave back to 6 years. What will this total amount be if interest is compounded yearly? So I changed it up on you here a little bit. I said interest is compounded yearly. Well, you will get this formula on the test. Remember, compounded yearly means n equals 1. That's the number of times you compound interest in 1 year. My principal is $145,000. R is very interesting. It's 0.35%, which means 0.0035 as a decimal. If you put in 0.35 or you get it somewhere that's so outrageous it won't even work. T is 6 years. Put this into your calculator. There you go. Make sure if certain calculators you put this in parentheses or do the math first. It's 1 times 6 there. Mr. Boseman, interest is compounded quarterly. So that changed my n to 4 this time in my formula. Now notice, the more times you compound interest, folks, the more money you should end up getting. It might not be a lot of money, but it's more money. Now, more money equals more problems, as the song goes, but we'll take the more cash in this case. And last but not least, Mr. Boseman compounds interest continuously. Continuously is the only time you will be using the PERT formula, folks. PE to the RT power. Principal is the amount of money you deposit. E is the number on your calculator. We've talked about that. That is Euler's number. It is 2.71828 and all that fun stuff. It is also located near the LN button on most of your calculators. It'll be like an e to the x, a tiny little lowercase e, or just an e in general. You type in 0.0035 times 6 for t is 6. There's my t. There's my r. Here we go. The only time you use this formula is when the word continuously is used. You now are ready to go. Go henceforth and do. You are all prepped for the test. So go henceforth and crush it. Commence.